Symbols are critical for technical communication. They are not dependent on any specific language, being international in scope and character. Hydraulic graphic symbols emphasize the function and methods of operation of components. These symbols can be rather simple to draw if we understand their logic and the elementary forms used in symbol design. The elementary forms of symbols are circles, squares, triangles, arcs, arrows, dots, and crosses. Click on each of the following categories to see how these common hydraulic graphic symbols are logically constructed, giving symbolic representation of its component. Critical to proper interpretation of schematics. Continuous lines indicate a working line, pilot supply, return, or electrical line. A dashed line indicates a pilot, drain, purge, or bleed line. Flexible lines indicate a hose, usually connected to a moving part. Lines crossing may use loops at crossovers or be straight across. Lines joining may use a dot at the junction or at right angles. A schematic is a compilation of graphic symbols interconnected, showing a sequence of operational flow. In short, they explain how a circuit functions. Correct schematic reading is the most important element of hydraulic troubleshooting. Although initially most circuits may appear complicated, recognizing standard symbols and systematic flow tracing simplifies the process. This circuit uses two sequence valves. They are normally closed valves that open at a predetermined setting. By tracing the flow in this circuit, we should be able to determine how this circuit is designed to operate. This process is called reading a schematic. Let's begin at the pump. Follow the flow past the relief valve to the directional control valve, which is shifted to the upper position as shown. The directional control valve directs flow to the lines in the upper circuit. Here, flow can go three places. The upper check valve blocks one passage. The closed sequence valve blocks another. But flow to the A port of the actuator is open. As the cylinder rod retracts, flow from the B port is blocked at the check valve, so it exits to the tank through the directional control valve. When the cylinder is fully retracted, pressure will build in the pilot passage of the sequence valve. It opens and sends pilot pressure to the directional control valve. Pilot pressure on the upper side of the directional control valve will shift the valve downward. Pump flow is now directed to the lower circuit, and the flow here goes to three places. It is blocked at the check valve and blocked at the closed sequence valve. But flow to the B port of the actuator is open. Flow in the port will apply pressure to the piston and extend the cylinder. Flow out of the A port is blocked by the upper check valve, so it flows through the directional control valve to the tank. When the cylinder is fully extended, pressure continues to build. Pilot pressure opens the sequence valve on the bottom. This sends pilot pressure to the lower side of the directional control valve, shifting it back into the upper position. Now, pump flow is once again directed to the rod side of the actuator to retract the cylinder, and the cycle begins once again. Tracing the flow in this circuit reveals that it is designed to keep retracting and extending automatically. Now that we understand the circuit, we may conclude that the proper function of the system will depend on the proper setting and function of the sequence valves, and the proper function of the hydraulically piloted directional control valve. This is a high-low circuit. Such a circuit would be used to achieve high speed or rapid advance at low pressure, followed by slow speed and high force. A good example of a high-low system would be a press, where the ram would rapidly advance up to the workpiece. At that time, the pressure starts to build. The flow from the high-volume pump is diverted to the tank. The low-volume pump would produce the little flow needed to continue moving the ram into the workpiece. The pressure will continue to rise until it reaches the relief valve setting. When the directional control valve is reversed, the pressure drops and the unloading valve closes. The cylinder would retract at a rapid speed. Now let's examine more closely the components that make up this system. First, the unloading valve. This valve has been set at 500 psi. When the system pressure reaches 500 psi, this valve will open and allow the flow from the high-volume pump to go back to the tank at minimal pressure. Next, we will look at the function of the check valve. When the system pressure is less than the unloading valve setting, flow from the high-volume pump flows through the check valve to combine with the flow from the low-volume pump. After the unloading valve opens, this check valve closes, so that the flow from the low-volume pump won't flow to the unloading valve. Now, let's take a look at the high-low pump group. This is a double pump. These pumps have a common inlet and separate outlets. During low-pressure rapid advance, both pump flows are combined. When the unloading valve opens, the large pump's flow returns to the tank, and the small pump's flow is used to do the work. Finally, we will look at the system pressure relief valve. This valve limits the maximum system pressure. Notice the schematic shows the pressure at which the valve should be set. Now, watch as these components work. In our circuit, the cylinder has a weight that would cause it to free fall or drop at an uncontrolled rate. A counterbalance valve is placed in the rod end port of the cylinder to apply back pressure. The back pressure is the result of the load trying to force the fluid out of the cylinder and through the counterbalance valve, which is closed. The counterbalance valve has to be set slightly above the load-induced pressure. When shifted, the directional control valve applies pressure on the cylinder piston. This, in turn, increases the back pressure, causing the counterbalance valve to open, allowing the cylinder to lower the load at a controlled rate. Now let's examine more closely the components that make up this system. First, we'll look at the offline or kidney loop filter circuit. This circuit consists of a pump motor group, a filter, and an air-to-oil heat exchanger. The pump draws hydraulic fluid from the reservoir, passing the fluid through a filter and an air-to-oil heat exchanger. This circuit usually runs continually to keep the hydraulic fluid clean and cool. Next is the pressure-compensated pump. The pressure-compensated pump de-strokes when the directional control valve is centered. At this time, there is pressure being maintained between the pump and directional control valve, but no flow. When the directional control valve is shifted, the pump goes on stroke, providing flow for the circuit. Next, we have the directional control valve. This is a 3-position, 4-way valve with a float center. This valve, when centered, will block flow from the pump so that pressure will build and de-stroke the pump. Both work ports are routed back to the tank, so there is no pressure in the work port lines, except between the rod end of the cylinder and the counterbalance valve. Now, we look at the counterbalance valve. The counterbalance valve maintains back pressure on the rod side of the cylinder so that the cylinder brings the load down at a controlled rate of speed. The check valve is used to lock and hold the load on the cylinder when the directional control valve is centered. Now, let's watch the system work again and see how each component operates.